Hello, welcome back. I'm Jason. Now, this is a very personal video for me. In truth, I debated on even making this video for many years. I wanted to make it several years ago, but never got around to it, kept kind of putting it off because I didn't know how to actually structure it and how to actually tackle it. But the main theme of this video is to share with you my math struggles, my struggles in learning science, math, and how I overcame those struggles to be where I am today. If there's one thing that you take away from this video, it really is that there's really no such thing as like math people, with very few exceptions I'll talk about in just a minute. But most of us, if we're not too good at something, we can practice and we can overcome it. Because believe me, if you're struggling in math or if you're struggling in physics, I was in your position. I know what that feels like. So what I'd like to do here today is I dug up my grades all the way back in third grade, all the way to college, and you will see that I was a very poor student, but there was a progression along the way. So I want to show you my grades. I have my report cards all the way back from third grade all the way to college. I want to show you the progression of my journey, my thoughts along the way, and then most of the video I'd like to share with you my top tips and strategies from teaching millions of people over the years in math and also in one-on-one and my own struggles as well. So what are my top tips? What are my top strategies? What do I think is important? Because at the end of this video, I really want you to succeed. I know what it's like to be frustrated and I really want to help you overcome it. Now, before I go back in time and show you where I started and all of the struggles with my grades along the way, I'd like to share with you where I ended up kind of from a today point of view. So I went to university and got a Bachelor of Science in Electrical Engineering. And for those of you who don't know, when you take any branch of engineering, but especially electrical engineering, it's very math heavy. So it's not a mathematics degree, it's kind of an applied math degree. Of course, applied to, electricity, magnetism, communications theory, circuits, all of that stuff. Computer engineering is all rolled up into electrical engineering. And I ended up with an A average with my bachelor's degree. All right, I did work for a short period of time in between the bachelor's and the master's degree, but I did go back to graduate school pretty soon after my bachelor's degree, and I got a master's in electrical engineering. And in my master's in electrical engineering, which I did in Austin at University of Texas, I got an A average in the grades, and of course you have to do a thesis and research as part of a master's degree. All right, now I've got some work experience in there. I want to get back to the work in a minute, but I went back when I was working at NASA and I got a master's degree in physics. Right? You got to remember, I wanted to be an astronaut. There's a whole nother video as to why that didn't pan out for me. A lot of it had to do with the space shuttle program and the timing of when I came in. But I went back and got a master's degree in physics and I got an A average. So working on mostly relativity theory and such is what I did my thesis on for the master's degree in physics. So BS electrical engineering, master's electrical engineering, and master's in physics. Now, I told you I'd come back to the work experience. As an undergraduate, I did work in a chip fabrication company that I was tasked with learning how to disassemble computer chips, actually dissolve the packaging around the computer chips and look at the computer chips under an electron microscope, various kinds of electron microscopes. So I got pretty proficient with using scanning electron microscopes and also transmission electron microscopes and really measuring how the chips were manufactured. Now, after graduation, I worked for the same company in a totally different area, designing computer boards for signal processing chips. So any cell phone that you have, any computer, any laptop, they have these signal processing chips, and I sort of learned how to design computer boards for those. Now, when I was in graduate school for my master's degree in electrical engineering, I worked in concert with the physics department on a project with NASA. So that was my first exposure to working with NASA on a plasma propulsion rocket for deep space propulsion. So basically it was a gas that you would heat up with an antenna, it would ionize the gas, and you would use magnetic fields to channel the exhaust out the back. And so we did a project about that. The project was ongoing for many, many years. In fact, one of these days I'll probably do a video just on that, because that's really fascinating all by itself, why plasma thrusters are very efficient for really deep space travel. All right, now after I got that master's in electrical engineering, I was very lucky to land a job at NASA. So that was sort of my dream job. Remember, I wanted to be an astronaut, so I was getting closer and closer and closer to NASA, and I became a flight controller for the space shuttle. I was there for about 8 years, and I really consider my entire time at NASA to almost be like another graduate degree. You walk in the door, you don't know anything about spacecraft really, other than the general stuff people know, and you come out the other end being as much of an expert as is possible on these systems. Right? I didn't know everything about the space shuttle. Nobody knows everything. But in my system, I was an expert in the avionics system, in the computer systems and the flight control avionics for the space shuttle. Right? Now, there were 4 certifications that I achieved over the years there. Backroom certifications, support roles, and front room certifications in mission control that you see on TV for the orbit phase of flight and for the ascent entry phase of flight. Now, while I was at NASA, I was always tinkering on the side with various things. I started to build an airplane for a while there, got pretty far into that, and I started dabbling in video. You got to remember, this is sort of before YouTube became really a big thing, actually before it became anything. I was dabbling in video, and I started to record myself doing these algebra lectures. And you got to remember, there's no streaming services, so I would burn these lectures onto a CD or a DVD, and I would mail them out to people and charge them a very small fee and just teach them algebra. Well, after I did the algebra, I did some calculus, and then I did some physics, and I did some chemistry, and I did some advanced calculus, and just kind of like went on and on and on. And eventually I had like this whole library of lectures and of problem-solving sessions. And I learn best, it's going to be one of my things I talk about here, I learn best by solving problems. So I kind of put that and poured myself into that and built a very small business while I was working at NASA. Now that became a small business, and then a medium business, and then a slightly bigger business. And over time, it became apparent that the space shuttle program was going to wind down, and the timing really just wasn't right for me to try to become an astronaut. There's an age beyond which you're really just not going to become an astronaut. And I was bumping up against that age, and the shuttle program was ending. So I had to make a decision. And I could have absolutely stayed at NASA. I could have been a manager. I could have been a flight director. I could have done lots of things. And I do have, some, of course, thoughts like what would have happened if I had stayed there. Of course, I missed the place, right? But I chose to go and teach full time and to embrace this thing called YouTube, which was becoming bigger and bigger and bigger. Of course, now it's huge. And so I started a YouTube channel, started a website, started a streaming service, and that's where I'm at today. And I can confidently say, this is not really bragging, this is just facts. I can confidently say that I think I've helped millions of people in math and science, based on the number of YouTube views I have, based on the number of subscribers I have, based on people that email me. I think that's a thing that I can say with certainty. But here's the thing. I've interacted with thousands and thousands and thousands of people on email and other ways. And most people assume that I am just a super gifted math person. And the truth is, I'm really not a gifted math person. Believe me, I've actually met real gifted people in math. I met them in graduate school. I met them at NASA. There's some really bright people at NASA. Some people are just born, a very small percentage, they're just born latching on to that. Just like some people are born and they're really great at art at a young age, prodigies, right? There are a few people like Einstein, like Isaac Newton, you've probably heard of him, Richard Feynman, John von Neumann. There's many people out there that you can go and read about. Euler, the famous mathematician Euler, that were truly savants or, just prodigies, right? I'm not that person. I'm going to show you in a second my grades. And my grades were not good, right? But I learned the process of math. I wanted to learn math because I wanted to be at NASA. I wanted to be an astronaut. I had my motivation, right? And so it took a long time for me to channel that in the right direction. But I'm the poster child for somebody who was not a math person, who didn't get it. And I've got the receipts to prove that to you, but that overcame it. And that's really what I want to do today. It's not to brag on my YouTube channel. It's to show you that somebody that you might look at and say, this guy's brilliant. He came out of the womb knowing how to do calculus. It's not true. And I'm going to prove that to you, and I'm going to give you the tips that I use to succeed. So in a nutshell, this is my story, for lack of a better word. Now I want to share one story with you before I kind of get into the meat of this. It's vivid, and I carried it with me my whole life. I have a very strong memory of being in probably 4th grade, getting very frustrated trying to solve some problem for a test or a worksheet or whatever in class. And I was so frustrated, I had to sharpen my pencil, and I walked over to the pencil sharpener, I sharpened the pencil, and I was thinking about it, and I was so lost, and I was so mad, and I was so frustrated that I took the pencil and I snapped it in half, and so I didn't even have a pencil anymore, and I had to get another one. I was so angry. The emotions just overwhelm you when you can't get something like that. So if that's you, or if you've ever been even somewhat in that direction, I feel your pain, believe me. And to be honest with you, I think that's why I'm pretty good at explaining things. It's because I know what it's like to have no idea what you're doing. And so I can build you up from nothing to something. And so let's get started. I like to share my journey with you and how to do that right now. All right, we're going to start out with 3rd grade. You can see my grades in math. C, C, B, C, C, D. So D math student. C, C, C. 4th grade. And again, we're going to go to mathematics. Not very much improvement. C, D, C, B, B, C. So I guess you could say a little bit of improvement in that I got a couple of B's there. But in general, I would say not a great student. Okay, 5th grade. We have an 82, that's a B. A 72, a 56, that's an F in math. 88, 70, 82, and for the year, my final grade was an average of a 75, so not great. Let's look at science. 82, 71, 55, 76, 79, 83, 74. Here is the last year of middle school, which was 8th grade for me. And here is science, 80, 70, 72. And then when we get to math, solidly below average, 77, 82, 86, 76, 95, 86. So I guess you could say I improved a little bit. All right, now between 8th grade and 9th grade, something changed inside me, seriously. This sounds sappy, but it's true. I wanted to be an astronaut, and I knew that it would never happen if I didn't get better grades. I'm pretty sure the reason why my grades were so bad is just because I spent all of my time just trying to cut up and make friends. And we moved around a lot, and I was just always in that process of just trying to earn laughs and giggles from everybody else. But when I got to 9th grade, I made the self-imposed decision that I have to try harder. I just somehow grew up enough to realize that I had to make this change or nothing would happen. Now, for me, it was becoming an astronaut. And so people that maybe talk about the space program and say, oh, it's expensive or whatever, trust me, it's not. I could go into a whole video about how inexpensive our space program is compared to other things. But even putting aside the price of that program, if it inspires some people to do better, then we are benefiting our society from it. For me, it was the space program. For you, it might be being a doctor, or it might be being anything. It doesn't even have to be a STEM field. It could be the best choir director that you can be. It can be getting into a program in the military. It could be doing whatever. If I have one piece of advice for young people, is find something you love. If it's art, it can be art. If it's football, it can be football. If it's physics, it can be physics. If it's chemistry or astronomy or whatever, it can be any of those things, but find something and hold on to it because it can carry you through into adulthood. So over one summer, I then joined 9th grade, and you can see from my math grades in Algebra 1, 95, 96, 96, and then we had 93, 94, 98. So absolute improvement from middle school to high school. And then when we go over into geometry in 10th grade, 90, 97, 94, so mostly A's. So it was a B here and there in math. And in science, it's A's across the board. Here we have 11th grade, Algebra 2, 96, 97, 90. Not so great on that exam there, but then moved on to 96, 87, 89, and so on. So mostly A's, a couple of B's thrown in here. And then finally, senior year of high school for pre-calculus, 98, 96, 100, and then 96, 93, 99. So solid A's across the board. So you can see the progression from elementary school being very poor and then slowly progressing through and doing better, right? I'm going to show you how I did that in just a second. But before I do that, I don't have my undergraduate transcript from electrical engineering, but I do have my graduate transcript in electrical engineering. So this is what I took. Electromagnetic field theory, A. Plasma processing of semiconductors, A. Antenna theory, plasma processing, number 2. Lasers and optics, plasma physics, satellite communications, research, all A's across the board in graduate school. Now, my undergrad grades were similarly almost all A's, a couple of A minuses. The purpose of doing this is not to brag. Again, most people think I'm a whiz since birth, but I'm trying to show you that I'm not. And so if you're struggling, please know that there is a path for you to overcome this as well. So without further ado, here is my long list of things that I really want you to try to take to heart. How anyone can come from being very frustrated to doing very, very well. But it is not a quick process. It is not a, oh, I'm doing great today. It takes time. All right, let me start with the first thing. And that is, I want you to master the fundamentals of what you're doing before advancing on to other things. In other words, knowledge gaps or lack of skills end up compounding very quickly. And that is the reason why you feel lost. Right? Let me give you a concrete example. In my experience in algebra, calculus, whatever, if a student doesn't understand what's going on, it's usually because they have basic problems that they never mastered. And in my opinion, in my experience, most of the time, the wheels start to come off the train when you get to fractions. When you get to fractions around 4th or 5th grade and you start adding fractions, dividing fractions, multiplying fractions, simplifying fractions, all these things, usually if a student can't master that, or if a student kind of barely got through that, then they start flunking algebra pretty bad. Because in algebra, you have fractions, but the fractions have letters in them. So of course you're not going to be able to do anything if you don't even remember or ever really even knew how to deal with fractions as a younger person, right? Also, long division, when you learn how to divide numbers, I hated that in 3rd or 4th grade, 5th grade, I guess it was. Right? But when you get to algebra, you're dividing and canceling terms all the time. And if you don't know how to do that, then you can't do it in algebra. And then you can't do it in calculus. And then it goes without saying, if you're doing poorly in algebra and calculus, then you can't do well in physics because it's all applied math. And you can't do well in chemistry because it's calculations all the time. Now, as far as multiplication and division goes, when you're a younger person, I want you to memorize your multiplication tables. 8 times 8, you should know what that is. 7 times 6, you should know what that is. You don't think about adding them. You learn the process, but you memorize those tables, because when you do division, you go backwards and you're asking yourselves, okay, 6 times what is 24? And you have to know that. And you can't go down to counting lines on your paper for everything. So some things you have to memorize. Multiplication tables is one of them. Get some cards, memorize them. Fractions, you must be proficient in how to add fractions, divide fractions, multiply fractions with numbers. Let me give you an example of how important that is. Now, you learn when you're younger that if you have the fraction 1/2 and you add to it the fraction 1/2, and you learn that in order to add fractions, you have to have a common denominator. That is a super foreign thing when you first learn it. Because when you have 1/3 plus like 3/4, the bottom number, the denominators are different, and you have to make them a common denominator first, right? So I don't want to get into a whole math lesson here, but I'm just reminding you of that so that you know that 1/2 plus 1/2, and you learn that if the bottom numbers are the same, you keep it. So the bottom denominator is a 2, and the numerators, 1 plus 1 is 2. So you get 2/2, and you know that 2/2 is the same thing as 1, as one whole. So 1/2 plus 1/2 of a pizza is a whole pizza. That's what that means, right? Now, the reason why that is just a single example is so critical is, let's move on in life a little bit until you're in algebra, maybe even algebra 2. What if I give you the fraction 1 over x plus 1 plus 1 over x plus 1? If I give most students that in the beginning, it looks scary. Why? Because it's a weird fraction. Because the denominator has an x in there, and it's not just an x, it's an x plus 1. And it also has a parentheses there, which is foreign in the beginning as well. All right? But if you look at this more critically, and you know how basic fractions work, then you know that it's just a fraction plus another fraction, and the same rules of fractions apply. So in this case, the denominator is x plus 1, and the other denominator is also x plus 1. So you keep it in the final answer, just like you do for numbers. X plus 1 is the denominator of the answer. Then you can add the numerators. So you have a common denominator here. 1 plus 1 is 2, so the answer is 2 over x plus 1. Now, if you don't know how fractions work, then this seems impossible to understand, and it looks very complicated. right? Also, what if the denominators were not the same? What if I changed it so that it was x plus 1 and then a different denominator for the second fraction? Then because you know how basic fractions work, you know that you have to get a common denominator, just like you do for numbers. And because you work with numbers so much, then learning it for letters and numbers is not as hard. And so we take you through that. So the first bullet point here, I'm expanding on it so much, but basically is, do not move on in things until you really get something, right? And because these gaps in knowledge and skills, they compound. Because if you don't know how to add these fractions, then you can't, these algebra fractions, then you can't solve any equations of any complexity because you don't know how to manipulate anything. And then you can't do anything in calculus. And then you can't do anything in physics, and then you've walled off. And then you have walled off all of math and science, all because basically you didn't understand basic fractions. So if there's ever any doubt, go back to the basics, fix the gaps, then move on. That's tip number 1. Probably the number 2 tip, which is really just as important as number 1, is I want you to focus on understanding concepts and not memorizing formulas. Believe me, I was there. I used to try to memorize all these physics formulas, and some of them you will memorize without trying because you use them so much. But memorizing, if it's 1/2 mv squared for kinetic energy, is not that important. It doesn't matter if you really have it memorized. What matters is that you understand the concept, that in physics there's this concept called energy, and that there's 2 kinds of energy that we see in the world. One of them is called kinetic energy. That's the energy of motion. That's 1/2 mv squared, right? I happen to know that because I've used it for years. But if you don't remember that, all you really have to remember is that there's a kinetic energy, which you can look up, and that's the energy of motion. And then there's potential energy, which is the energy of some system that it can do something in the future. For instance, if I take this bowling ball, if I have a bowling ball, and I bring it to the top of a building, it has a lot more potential there than it does down here, because if I throw it off the side, then it can impact the ground and do some damage. And so potential energy is like stretching a rubber band. It has the potential to do work, and work is something else that we learn about in physics. And then when you learn the concept that there's a potential energy and kinetic energy terms for almost every system in the world, in the universe, then what you learn is that the total energy of a system is really unchanged. We call it conserved, law of conservation of energy. So the potential energy plus the kinetic energy of a more complicated system usually just never changes. Think of a roller coaster. A roller coaster goes to the top, very high potential energy. But then when the roller coaster gets to the bottom of when it picks up a lot of speed, it has less potential energy, but it has a lot of kinetic energy because it's moving fast. And as the coaster goes up and down, it's trading kinetic and potential energy, just like a fighter pilot taking an airplane up and down like this is going to be trading potential and kinetic energy. But the sum total of the total energy of the system doesn't change. You're just trading it between different forms. And then that concept of trading different kinds of energy, it comes in handy to understand more of science down the road. When I slap my hands, I hear it. The hearing it, that is a sound wave coming through the air, but that's an energy transfer mechanism. My hands are hot. Some of the energy goes into vibrating the air and vibrating them through the medium and hitting my eardrum, and that's a dissipation of energy as well. So it's concepts, not formulas. I'll give you another example from calculus. We learn about derivatives for the first half of Calculus 1. You know how to take derivatives, but do you know how many students I've talked to that could calculate derivatives but really didn't know what they were? Or that could calculate integrals and had really no idea what it meant? Okay, you have to know what they mean, right? Because that's more important than anything. A derivative is the slope, just like the slope that you learn in algebra, the slope of a line. But in calculus, we learn how to find the slope of more complicated shaped curves. Because in real life, things don't just travel in a line. A rocket will take an arced path into space. Any number of things, they in general don't follow straight lines. So in calculus, a derivative tells us how to find the slope of a curve that is always changing. What does that mean? How do you do that? And what is the derivative? But as a concept, it's the slope of the line that is tangent, which means barely touching in one position, the curve that you're interested in, right? And it has applications in literally everything. And the same thing for the other half of Calculus 1, which is called an integral. An integral, which is also called an antiderivative, is basically a way to add up an infinite amount of tiny, tiny objects. Now you might say, well, you're talking about infinities, you're talking about, okay, all this stuff we get into in calculus. I'm just giving you the overview. A derivative is the rate of change or the slope of the line tangent to a curve. An integral is a mathematical way to add up an infinite amount of tiny, tiny things. You might say, why do I care about that? Well, literally everything becomes an integral in real life. Because in this room is a trillion gas molecules. I can't really count them all, but I can write down some formula that governs maybe the pressure in different parts of this room. And then if I make an integral over the pressure, over the room, over the volume of the room, then I might be able to calculate like the force of the gas or something, because I'm adding up an infinite amount of tiny, tiny things. The tiny pressure at this point, and the tiny pressure at this point, and the tiny pressure at this point, and you add them all up and you might then get the force of the gas on the container. Or if you're talking about electricity and magnetism, you might be adding up the magnetic field over a region around a magnet. But it's a continuous field that always changes all the time. So you write down a function that describes the field at every position, and then you integrate, which means you just add up the contributions of all the parts of the field over an object. It literally is like 1 plus 1 plus 1 plus, it's just literally adding things up, but an infinite number of them which are very tiny. That's what an integral is. You need to have the concepts. Then, when you get to more complicated things in engineering and an integral pops up on the page, you will know, oh, they're just adding something up. That's what the integral means. If you see a derivative, you're going to say, oh, they just want to know what the slope of this function is at this point. And you will have a concrete internalization of what it means. My next tip is one of the most important, and that is I want you to draw a picture or a diagram to visualize your problem, whatever problem it is, no matter how simple this problem is. Every single problem, certainly in physics, and a lot of times in chemistry, and definitely in engineering, you have to draw a picture. Even if you think it's simple, because sometimes the problems are set up in such a way to trick you. And the reason they trick you is because if you don't draw the picture, you don't understand what's missing. You don't really have a good way. This is what leads to paralysis on exams. If you're on an exam and you read the problem and you just don't know what to do, then you've never trained your brain that step number one is always to draw a picture. No matter what, even if the picture is silly, if you look at my pictures I draw for solving problems, they're silly. I can't draw anything. If you're trying to draw a rocket, draw something that looks kind of like a rocket. If you're trying to draw a person throwing a rock, draw a stick figure. If you're trying to draw something going through the air, draw something with a dotted arced line. But whatever you do, draw something. And then when you get the drawing down, you write down everything you know about the problem that fits into the diagram. The velocity of the baseball, you draw an arrow with a velocity and the meters per second there. Gravity is acting down at 9.8 meters per second squared. You draw that acceleration and you write that down. The temperature of the gas, you draw the gas molecules inside of a container and you put the temperature of the gas. It forces you to write down what you know, which is incredibly important. So if I ever see my own kids trying to solve a problem without drawing a picture, then that's always what I'm telling them to do immediately, so always do it. All right, my next tip is do not skip steps ever. Always show every single step. And I run into this with my kids all the time. They know because the problems are a little bit simpler in 6th, 7th grade. They're a little bit simpler, so their brain can kind of get to the answer. And you're training your brain that you can kind of get to the answer. And so like a very simple equation, like if I tell you, x plus 1 equals 7, right? Well, you know what x is because x can be some number, right? X plus 1 has got to be 7. And you know that x has to be 6 because 6 plus 1 is 7. And so a lot of times you'll just write the answer down. The problem is this trains your brain that you're supposed to think through to the answer in your mind before you do anything. That is what kills you later on. Because when you're in chemistry or you're in engineering or you're in physics or even if you're in calculus, you don't have the mental capacity to think through which way do I have to go to get to the answer? Which way is the correct way? Now, there are exceptions. I mentioned some of them earlier, the Feynmans, the von Neumanns, the Einsteins, the Newtons, I can go on and on. There's the Eulers, and even people I've met in the past that are truly gifted in math. There's a very small percentage of those people that can maybe hold it in their brain. Most of us can't. So draw a picture, but don't skip steps in the solution. If it's x plus 1 equals 7, you write that down. The next step, what do? I got to subtract 1 from both sides, so I'm going to do that. And you're training yourself then that every problem requires steps. And you're training yourself that the first thing you write down is what you know. You rewrite the equation. Then the next step, you have to figure out what is the next logical thing to do, and you do that. And then you do the next and the next. Because getting to a solution is not a one-step thing, it's a sequence of steps. And the reason why you get paralysis during an exam is because you can't figure out in your mind how to get there. That is normal. That is not failing. That is just being human. So you train yourself to draw a picture, write every step, even for simple problems. Then when the problems get more complex, then you've trained your brain and you just go in order and you go in steps, and then it is tractable. Now this next one is one of my favorites. I want you to practice explaining concepts in simple terms. There's a couple of ways you can do this, right? This is probably the best way to actually internalize something. In fact, Einstein, I don't remember the exact quote, but he had a similar quote basically saying, if you can't explain something to somebody else in simple terms, then you don't understand it yourself. And that's what I find to be true. If I'm trying to explain something to my daughter or my son, and they're like, how does this work? And I'm like, then I don't understand it. If you can't break it down into simple terms, then you don't understand it. That doesn't mean you failed. It just means you didn't understand it, right? And all of us have to work at getting better at that. So if you can find somebody to talk to and explain to, do that. But if you don't have anybody like that, like if you don't have a study group or anything like that, then talk to yourself. If you had a hidden camera on me all the time, you would find me talking to myself all the time. I always tell people that I am the best listener that I've ever met, because I'm always listening. I'm patiently listening to myself, right? I'm talking to myself all the time. I'm verbalizing. How does this work? How does that work? And I think it's something to do with verbalizing and going back into the ear that trains the neural net to organize information for me. It might not work for you, but I recommend trying it. Now, if you're in a study group, usually there's the strong students in the study group, and then there's the weaker students, the students that don't understand as much. I was in several study groups like that in college, not so much in high school, but in college. And of course you can't do that every day because then you'll never have any time. But I made sure to go to those because I would have the weaker student. I mean, he wanted to learn. He just didn't know, well, how does this work? And he never, put it together. He didn't have, maybe his teachers that helped him to build these skills early on, or just never made the connections. So then it would force me to say, well, it's kind of like this. It's kind of like that. Remember when we did this? And then it's sort of like that. That building on our intuition, verbalizing it to somebody else, making you, for lack of a better word, vomit it out and get it out in a simple way that someone else can understand. It helps you organize your own thoughts on the subject. An example of that might be from quantum mechanics, for instance. I mean, I'm not an expert in quantum mechanics. I took quantum mechanics. I can calculate things in quantum mechanics, but do I think I know everything about quantum mechanics? No, I don't. But the way that I internalize things is to try to explain them simply, as simple as I can anyway. So in quantum mechanics, there's this thing called a wave function. You might hear that and say wave function and be immediately scared, but just stick with me for a second. So a wave function is just a mathematical equation that we write down that is in the shape, the mathematical form of a wave. But it's a little different than most waves because it has complex numbers for the amplitude and complex numbers for the phase, which just dictates what the thing looks like. And when I say complex numbers, I'm talking about, back from algebra, you learn about imaginary numbers and real numbers. A complex number is the combination of a real number and an imaginary number. So you see, I'm already building, right? You learn numbers, and then in algebra you learn imaginary numbers, and then you learn complex numbers, which are combinations of the two. And now we're building a function that is similar to a wave, or has a wave form, the form of a wave in mathematics, but that has a complex amplitude and a complex phase, which just talks about what the shape of the thing is. Now, this wave function in quantum mechanics, it represents something. And it represents, in quantum mechanics, the probability density. That just means a function that represents the probability in different locations in space of something happening. Usually it's like an electron or a photon or whatever you're trying to measure. It's the probability of something happening. Now, I'm skipping a lot of stuff because in order to actually calculate the probability, you have to square the wave function, and then you have to use calculus to integrate the wave function. Now, let's do what I just preached to you a second ago. What did we just say an integral was? You may not remember, but that's okay. If you don't, that's fine. You can watch the video a few times. An integral is a way to add things up, like adding up the pressure in this room to come up with the force on the walls, let's say. So if this thing's a probability density, and we're adding up the wave function by means of an integral, when we integrate the square of the wave function, what we're doing is we're adding up the tiny little contributions of that wave function over the space of what we're talking about. And so we're going to end up with getting the total probability of finding the electron in this region. If I want to know what's the probability of finding the electron right here, then I would integrate the wave function. I'm leaving out some steps here. I would integrate it over this volume, and an integration is the addition of a tiny little contributions over some region. And what we get out of that is the probability. So you always hear about quantum mechanics being about probability because the wave function governs the evolution and how the system changes over time, right? And when you measure something, you're essentially going to find the probability by integrating the wave function, which talks about the concept from calculus. So notice how I verbalize that, right? Now, as you learn things, maybe not quantum mechanics, but anything, verbalize it to yourself until you feel like you can explain it to a third grader. And then we talk about more complicated things and try to break them down as simple as you can, and that helps you learn the material better. Another example of that would be from like electric circuits. You've probably heard of voltage, you've probably heard of current, electric current, and you've probably heard of resistance. All right, so if I were trying to break that down into simple terms, I would use analogies. I would say, okay, so just like in a garden hose with water flowing through a garden hose, right? There's some kind of pressure pushing the water. So in a circuit, the pressure or the force acting in the electrons in the wire is what we call the voltage. It comes from the electric field. Where does that come from? It comes from the battery that's hooked up to the circuit or from the wall, which is generated from the power plant, which is something usually in motion. It's got to be a hydroelectric thing or photons hitting a solar panel or something is moving somewhere to generate that electrical pressure. So pressure is basically voltage, which is pushing on electrons. Now the electrons are in the wire and in the circuit, and they are the things that actually are moving and being pushed around. That is what the electric current is. It's like the water moving around in the garden hose. And then if there's any obstacles in the way, like a kink in the water hose or a resistor in a circuit, then that resists or constricts the flow of the electric current. So once you know that the voltage is the push and the current is the flow of the electricity, and the resistance is the resistance to the flow of the electricity, then you are in a better position to understand Ohm's law, which relates the voltage, the current, and the resistance together. So as you learn these things, I want you to verbalize them in a similar way as I'm doing here for you so that you can learn things better. I'll give you one more example real quick. We'll talk about electromagnetic waves. Most people would agree that's a complicated sounding thing. I agree, it's a complicated sounding word, but let's break it down a little bit. So there's this thing in the universe that is called an electric field. An electric field pushes on charged particles, pushes on electrons, pushes on protons. It's a field that permeates space in every location. This is a theory. This is a model of reality, okay? Electric field. And there's this other thing called a magnetic field. You all have heard of magnets, right? It also pushes on charged particles, but in a sideways direction. So oftentimes the particles will orbit and go around the magnetic field lines because the magnetic field pushes in a sideways way, whereas the electric field pushes in a straight direction, so to speak, to the charged particle. Now, these two effects, electric field, magnetic field, they were discovered more or less separately as separate things in nature, but then we started realizing that they were connected together. It turns out that when you start changing a magnetic field stronger and weaker, stronger and weaker, stronger and weaker, the changing magnetic field induces an associated electric field in the same location as where the magnetic field is changing. But here's the crazy thing. If you take an electric field and you start changing it by maybe charging or discharging, more charges, less charges, more charges, less. If you start changing the electric field stronger and weaker, then it induces a magnetic field in that location. So there's a duality here. You have magnetic fields, when they change, they induce or cause electric fields. And then you have electric fields, when they change, they induce or cause magnetic fields. So electric fields, when they change, can can cause the other field to happen. Magnetic fields, when they happen, when they change, can cause the other field to happen. And they kind of feed off of each other. Now, because of all this stuff, when you go through all the math, what happens is that if you make a wave out of an electric field, it can induce a corresponding magnetic field. But when that one changes, it creates an electric field, which is then changing, which is creating the magnetic field, and they kind of reinforce each other. And that is what a traveling electromagnetic wave is. It's a traveling packet of changing electric fields and magnetic fields. Now, of course, I'm throwing these in there because I want to teach you something too, right? To make the thing interesting. But I'm also doing it to show you how I'm internalizing these things. And of course, the first time you read something, you're not going to maybe break it down so simply. But by getting different perspectives, cogitating, thinking about it, solving problems, you will build your own model of how things work. All right, my next tip is when you're solving a problem, I want you to break the problem into simple steps. This kind of goes back to what I talked about before. The first step is always to draw a picture. The second step is always to write down what you know from the problem statement. If for instance, you have some problem like the initial velocity of a baseball is blah, blah, blah meters per second at an angle of 34 degrees or whatever, and this thing travels a certain height above the air, or it's on Mars with a different value for the gravitational acceleration. You write all that stuff down. How far will the thing travel, or how high will the thing travel, or what will be the temperature of the thing after 10 minutes, or what will be the electric field intensity at this location. Whatever it is, you write those things down, and then you have to decide what to do. You have to break the problem into steps. You have to stop the training that you've had when you're in third grade to get the answer in your mind. You can't do it when you get to higher level stuff. You have to instead think, instead of how do I get to the answer, forget about that. You can't do that. You have to ask yourself, what is the first thing I can do? I mean, after you've written everything down, what is the first thing I can do? Okay, I don't know how to find how high it goes, but I know how to figure out maybe the velocity, if it's a rocket, the velocity of the rocket when the engine cuts off. I know how to do that because I have enough information for there. I don't know yet how that gets me to the end of the problem, but I know how to find this first thing. I'm kind of speaking generally because I don't have a specific problem here, right? But I'm just saying in general, you have a ball of gas and the temperature is whatever, and it's venting with a certain pressure and a certain temperature, and you don't know how to find the actual answer to the question. But what you do know how to find is how many molecules per second are going through the hole. Find that first. You're not totally sure how that's going to help you, but you know that you can legally find it. Find it. Then when you have that, you do the same process again. What can I find next? Okay, I can figure out how far this thing is going to go next. Okay, once I have that, I know now that I'm on Mars, I know that I can calculate blah, blah, blah next. And you inch your way to the answer. I'm telling you right now, I have solved thousands of problems in my life, and I almost never know how to get the answer right after reading the problem statement. Almost never. Instead, you train yourself to draw a picture, write down everything, and what can I find first? In chemistry, if you're trying to find out like how much stuff is being made at the end of this chemical reaction, like how many grams of carbon dioxide is produced or whatever, and you don't know how to do it because the reaction is like 5 steps, then you start at step 1. I know how to find this intermediate product. And then I can take that intermediate product and I can find another product. And you inch your way to the answer. So break the tendency in your mind to get to the answer in your mind. You can't do it. One step at a time is the way you go. Next tip. It kind of goes with what I said a second ago, but a lot of times, especially in physics and engineering, you might think that you're not given enough information to solve a problem. For instance, in physics, I used to beat my head against the table because a lot of times I thought I needed the mass of the particle or whatever to solve the problem because it's moving and they didn't give me the mass. Maybe there's a typo in the problem. Maybe they didn't do it. Maybe they're wrong. You know, you start thinking these things. So if you really feel like there's something missing from the problem they didn't give you, here's a pro tip for you. You probably don't actually need to know that. In every single case, it has never turned out that the problem was wrong in my case. It has never turned out that I was right and they were wrong. I mean, occasionally I found mistakes, but I'm saying if I thought something was missing, it just always turned out that you didn't need to know it anyway. Mass is the biggest offender of this. When things are moving, you think you need to know how much mass of something is. But a lot of times what you do is you write one equation down. Like for instance, kinetic energy is 1/2 m, m is mass, v squared. But then you might have another equation of motion, the motion of the particle through the air, that also contains the mass. But when you substitute in and actually solve the problem, you might find that the mass cancels on both sides of the equation. Now, when something cancels on both sides, in other words, there's a term with mass on one side and a term with mass on the other side, and you can divide it away and cancel it out. Just like in algebra, you can cancel terms on both sides, right? What that means is that the mass wasn't really important in solving the problem. The most famous example of that, here's my little remote control I have for something here. When I drop this, it's going to fall down and hit the ground in a certain time, right? If I take a very heavy object like a bowling ball and I drop it, it's going to hit the ground at the same time as this, assuming you ignore air resistance, because in a gravitational field, everything falls at the same rate, right? The mass of the object actually doesn't matter. You think it does, but when you go through the physics, it actually doesn't. If you drop on the moon a feather and a hammer, which astronauts have actually done before, they fall at the same rate and they hit the ground at the same time. The reason that happens is because the force of gravity acting down on the bowling ball is much higher than the force of gravity pulling on the feather. That is true. However, the bowling ball is much harder to accelerate. It resists the motion. It resists the tendency to move because it has more inertia. But the feather has less mass and it doesn't have as much inertia. So yes, the bowling ball is pulled down with a higher force, but it's harder to get moving. And those two effects are both related to mass, and it cancels. And so it results that mass doesn't matter, even though you thought it did. So if you feel like you're not given enough information, then just write down equations and see if what you think you needed actually cancels in the end. My next tip is get really proficient with units and dimensions, because it turns out that a lot of problems in science and even in calculus can be solved just by knowing the units, how to manipulate units. And when I taught all of my basic curriculum from 4th grade on in algebra, I introduced units, dealing with units. It has a fancy word. It's called dimensional analysis in physics. But that's just a fancy word. It just means working with units, okay? If you learn how to work with units, then you can actually solve very complicated problems just by knowing what the units are, right? Let me give you the simplest possible example. Let's say you're traveling at 5 meters per second, and you do that for 5 seconds. How far did you go? Now, of course, you could write down, most students, if you're new to this stuff, you might say, well, there's a velocity equation, and velocity is distance divided by time. So if I'm trying to figure out how the distance, I got to solve for this, and I got to go through the whole thing, right? But if you know the units, you'll know that if you're traveling at 5 meters per second, meters is on the top and seconds is on the bottom of a fraction. Remember I said everything is going to come back to fractions? And it does, because all units are fractions, almost all of them. And so you have to deal with fractions when you're dealing with units. So anyway, 5 meters on top, seconds on bottom. But you're traveling for 5 seconds, let's say, or 10 seconds, whatever it is. Do you multiply those numbers or you divide those numbers? I remember struggling with that when I was younger. Do I multiply, do I divide? Which way does it work? Well, if you have meters on top and seconds on bottom, and you know you're going for 5, let's say, seconds in the future, then you know you have to multiply these, because you'll have seconds on the bottom of this unit and seconds on the top of the other one. And that means they will cancel. And the only unit you'll have left is meters. So even without knowing the formula for velocity as distance over time, you know you have to multiply these, because it's the only way that the units will give you a unit of distance in the end. Now, I chose the simplest possible example here that I think anyone can understand. But you're just going to have to trust me. When you get into chemistry, you will be able to solve some very complex problems just by knowing the units. It's just that the units in chemistry and physics they're weird because you don't know them at first. In chemistry, you have moles and Avogadro's number, and then you get the liters and cubic centimeters and all these other things. But if you work with units, if you get good with them, then it will help you solve tons of problems in the future. All right, my next tip is try to estimate an answer. Not for every problem, but sometimes it's helpful to estimate the answers with a round figure so that when you do the full calculation, you can check and see if it kind of makes sense. So here's an example. Let's say you need to calculate a 14% tip on some bill at a restaurant. Well, it's kind of hard to calculate 14% unless you're a human calculator in your mind, but it's very easy to find a 15% tip, and it's even easier to find a 10% tip. So you can get a ballpark immediately right away. So let's say your bill is $80, $80. right? Well, 10% of that, just move the decimal, $80, 10%, that's $8. So if it was a 10% tip, it would be $8. But to get to 15%, which is way closer, how do you do that? Well, if you know 10% is 8, then you cut that in half. Half of 8 is 4, and you add it. So 4 plus the 8 is 12. So 15% is exactly $12. That's exact. But you were asked for 14%, so you know that the answer has to be a little bit shy of $12. I'm doing a very simple example here with tips, but I'm saying it applies to everything. You might calculate, well, if the baseball's traveling at 132 meters per second, it might be okay to just estimate 100 meters per second and then multiply by whatever, and you're like, okay, it's going to be a little bit more than that. And then in your mind, you know roughly what the answer will be, and then when you calculate it, you'll have a good, quick check on if you went in the right direction. My next tip is I want you to work through example problems, many example problems, without looking at the solutions. I want you to review your mistakes. I want you to understand where you went wrong and try to work the problem again once you figured out what you did. A lot of students will say, oh, I made a mistake here. Okay, go on to the next problem. But you got to train yourself, man. It's just like, shooting basketball or playing hockey or violin or whatever. I mean, you've got to practice, right? And the way you practice is you said, well, I added those fractions wrong. Okay, let me do that again. And then you train yourself to get the correct answers. And also, you will be wrong a lot at first. This is not failure to be wrong. That's called learning, right? It's called being human. You're going to add fractions in the beginning and you're going to get the wrong answer. But you can't be distracted or discouraged by that. You will be wrong. When you were a little kid, you were walking around falling over all the time before you could walk. When you were learning how to talk, you were babbling all the time. You were making mistakes constantly, but you didn't have an ego back then, so it didn't bother you. When you get to this stuff, you will make mistakes. That is not failure. That's called learning. All right, here are a couple of shorter notes I want you to internalize in no particular order, a little bit faster. I want you to do practice problems daily instead of cramming. I want you to, just like practicing violin or practicing cello or practicing football, you don't just practice one day before the game, you practice every day, right? You got to do that with your math. Don't cram for the test, practice every day. Study with peers, teach other people. Break things down into simple terms for someone else. Read the textbook before you go to class. Even if you don't understand everything, you will have an idea of where you get lost. And then when you listen to a lecture, even if you're like listening to my lecture, if you already kind of know what I'm going to say, then it will clear up the holes in your mind. Next, when you're in class, I want you to take good notes. A lot of people think they'll just remember it. I remember in class thinking, well, I won't forget this. This makes total sense. Trust me, 3 weeks later, you will forget one little tiny thing that's very important. So take good notes and review your notes. Here's kind of a big one I saved for the end. I want you to really practice connecting material that you learned in the beginning with new material that you're learning now. From physics, it might be learning the concepts of motion and energy. And then when you learn about pressure, you're learning that the pressure is really the movement of the gas molecules. The motion of the molecules having energy is giving rise to pressure of a gas, but that's connected back to the beginning of your journey when you learned about potential energy and kinetic energy. So connecting things together is exactly how you move forward. It's how you build intuition. It's how you build confidence. One more quick example, a capacitor in an electric circuit stores energy in an electric field. An inductor, which is a coil of wire in a circuit, stores energy in a magnetic field. So you have a device that stores energy in an electric field and another device that stores energy in a magnetic field. And I already mentioned to you earlier that these two types of fields can influence and interact with each other. So later on in circuits, when you learn that you can use capacitors and inductors to build something called a resonance circuit. That's a circuit that allows energy to be transferred very, very easily. That's how radios work, by the way. You're tuning a station by tuning and changing a capacitor and changing the resonant frequency of a circuit. If you think to a swing set, what is resonance? See, I'm connecting back to something simpler because I know that electric and magnetic fields might be hard for most people to visualize, so I'm connecting resonance in that circuit with the following. A child on a swing set. You push them. You know that there's a resonant frequency that you push at. to couple your energy directly into the child going back and forth. You don't want to push too fast and you don't want to push too slow. There is a natural frequency you push at to couple your energy in. Why? Because in the swing set case, you have potential energy when you go higher, kinetic energy when you go down to the bottom faster. You're trading between potential and kinetic energy. And so there's a resonant frequency that makes a very efficient coupling of energy between those two forms. Now, this is just an analogy, but it's the same thing in circuits. Electric fields and magnetic fields can couple energy efficiently back and forth, trading forms between the electric field and the magnetic field. That leads to resonance in a very similar way by analogy, connecting things that you learned earlier to learn and understand more complicated things. Now, here's my very last big suggestion to you. When you are studying for an exam or just practicing, lock yourself in a room, get away from people for a while, and grab a stack of old test exams or something off the internet, or if it's a textbook, the solved problems in the back of the book, whatever, and you lock yourself in a room and you solve problem after problem after problem. When I was in undergraduate for electrical engineering, I literally would lock myself in a room in the library, shut the door. Nobody knew where I was. No cell phones back then. Nobody knows where I am. And I hid away and I worked hundreds of problems. You're going to get wrong answers, but eventually you're going to start to see patterns. You're going to start to see, how do I start these problems? It's all the same way. I draw a picture, I write down what I know, I got write this equation down. Oh, there's that equation over there. Okay, I can combine them like this. And eventually you do it enough and it's just like me talking. This is so hard for a 3-year-old to talk like this. But I don't even think about talking now because my neural network is wired. You got to wire your neural network. You got to practice tons of problems, even if you're just practicing to solve problems that are in the chapter. If you're watching my lectures, watch me solve the problem, and then you grab a sheet of paper and you solve the exact same problem. Now, I know what you're thinking. Well, I just saw you work that problem. Trust me, when the problems get to sufficient complexity, you will not be remembering every single step. And even if you do, what you're doing is you're training your brain. I have to do this, and then this, and then this, and then this, because you remember. But then when you see one that you don't know, your brain remembers, I have to do this, and then this, and then this, and then this. You got to train yourself. That's how you do it. You solve problems. So that about wraps it up for me. I really wanted to make this video a few years ago, but kept pushing it off and pushing it off because I didn't know how to approach it. If I start talking about how many people I've helped in math and science, and it comes off as bragging. If I talk about my grades in college, it comes off as bragging. But finally, I had the idea that I should really open up the books and show you without just telling you how bad of a math student I was. I was not the guy that came out of the womb that could just do fractions. I struggled. I did not understand why we have to have a common denominator. I did not know what it meant to multiply a fraction. 1/3 times 2/3. What did that actually mean? I mean, of course I could explain it now, but that's because I've done it for so many years. I did not know that then. I did not understand the concept of long division because I did not know that in algebra and beyond you have to divide things. I did not understand why we have to solve equations. Why are there equations? Well, because I never solved one before. I didn't have a reason to. But now I know, because I've studied more advanced things, that we use equations all the time to model reality. And you're just trying to write down more equations that kind of match reality a little bit more closely. And as we do that, the equations get more and more complicated, and you need more tools in your tool bag to do that. But I was the poster child for the person who didn't do well, that I overcame it. And it's not because I'm a genius. If I can do this, you can do it too. I tried to outline the things that I think are the most important things. I really stand behind everything I've said here. But having said that, I really want to hear your thoughts. I want to hear your stories. Drop me a line. Let me know what you think. I've gotten emails, thousands over the years, from people. I've been doing this so long with my tutoring that I actually was tutoring people in 8th, 9th grade, with my videos, not with one-on-one, but with my videos, that have now since gone on to become attorneys, doctors, physicists and have connected with me and said, hey, you really helped me. And so I really, really, really like to hear that. I want to do the same for you. So please do drop me a line. Let me know what other kind of videos you'd like me to chat about, talk about, and produce. And please, as you go on your journey, the next time you get frustrated, the next time you want to slam the book shut, the next time you want to snap your pencil, the next time you want to just scream and say, I can't do it, I want you to remember I was in your shoes. Failing like that, quote unquote, is not really failure. It just means that you're learning. And when you figure it out, you will get a little bit of confidence each time. And with a little bit of confidence becomes a little bit more confidence, becomes a lot of confidence. And then one day you're going to say, I actually can do this. It's not that hard because you built your confidence. So please continue to work hard, drop me a line, and remember, always stay curious. Learn anything at mathandscience.com.